Okay, so I've got REU detection working, and now I have it not disturbing the data that's currently in the REU in the process of doing the detection. So I'm going to show you how this works. So first we'll use a little tool that came with the CMD REU called Zap REU. Okay, so this little utility lets you, for example, view the contents of the REU. So this is what the REU had when the machine first booted up. So it's basically just crap data. You can change the page. So this is the page we're looking at. You can see this kind of crap data. Or you can change the bank. So we can flip through the banks here. So what we can do is the tool lets us fill a range of the REU with memory. So we'll set the fill byte to be, something arbitrary, let's say FA. And we can set the end address, so this is bank 1F and then FFFF, and the start is bank 00000, so this is the full 2 megabytes. Now we'll hit B to begin fill. Okay, so now when we view, we can see that as we move through the banks, we move through the pages, everything is now just set to FA. So now, let's imagine that FA is legitimate data that we don't want disturbed. So we'll quit out of the program. Now, my original REU detection routine was actually disturbing the contents of the REU, as does the detection routine that I found on Codebase 64. So we'll run that first, which I've named old, just to see what it'll do. Okay, so REU found, available banks, hex 20, that's 32. Now we'll run our Zap REU utility again to see what has happened. Okay, so what you see here, so bank 0, page 0, the first 16 bytes has been zeroed out. The way that the detection routine works is that it first writes a set of random, well, not a fixed set of randomly chosen bytes into the first 16 bytes of a bank. Then it reads those, compares them to see if they actually got stored properly, and if they did, it increments the bank count. Then it clears out that bank so that it can detect when the bits roll over, and it's kind of complicated. I'll have to write a blog post about it, but basically, because this is only 2 megabytes, as soon as you roll the bank past 1F, it actually wraps back around to the first bank. And so, but there's no way to detect that except for to check to see if these are 0 or if they're those random numbers that we pre-filled. So if they're the random numbers we pre-filled, well then we've detected a new bank. But if they're zeros, we know it's rolled around. The problem is writing the zeros in there has disrupted our original data FA. So let us refill this again. So this time we'll pick another fill byte. Let's say, I don't know, F5, okay? Ending address. Okay, complete range again. Begin fill. We'll view our contents. Okay, so now everything is F5. So we can see everything's F5. Now what we'll do is we'll go back and we'll run the new version of the REU detect routine, which should not disturb the contents of the REU. Okay, REU detected. It detected hex 20 banks. We'll run Zap REU again. We'll view. Now as you can see, this time the FF has been maintained across all the banks and all the pages of the bank. So that's great. Basically, the way that it does this is there can be up to 256 banks, but we only actually write 16 bytes per bank to the REU in order to test for the existence of the bank. So what it does is it first backs up the content of that bank, the first 16 bytes of that bank, to main memory. Then it writes in the crap, then it clears it out, and then at the end it will restore the backup to all of the banks that were actually detected. And so for a 16 megabyte REU, that's going to have all 256 banks, but you only need 16 bytes per bank, and so you basically need 16 pages of main memory, and that's no problem.